In late 2017, I made a Machinist jack as a Christmas gift for a member of the YouTube Machinist community. The gift was part of a Secret Santa exchange. The recipient seemed to really enjoy receiving it, and the videos were quite popular. In 2018, the exchange happened again, and I decided to make another jack with the same design. I recorded much better footage and planned a much higher quality video of the build. Good videos take time, and for the last couple of years I always seem to have had another video in production which needs to take priority, so this one kept getting delayed. I've kept working on it though, and it's finally here. The recipient of the gift was Craig over at Craig's Workshop.
Hi, if you'd like to see a companion piece to this video which shows how to use this Machinist jack, then please check the links over there or down there. Thanks, speak to you soon.
Welcome to Adventures with a Very Small Lathe. The 2017 Machinist jack design was inspired by Phil Desjardins and Pierre Baudry, who made a number of jacks like this for Keith Fenner's What's in Your Box tool giveaway. The centrepiece of the tool is a screw with a large radius custom thread. The base has a centre hole with a matching thread, and between them they control the height of the jack. A cap fits on top of the main screw, and features machined into the top help it support different geometries in a stable way. The final part is a spacer, which can increase the height of the tool. All the parts have a free rotating stacking geometry machined into them, so the machinist can stack them to get extra height in whichever way makes sense. I've modelled the complete tool in OnShape, and a link to the design is in the description below, though I can't promise I stuck exactly to the dimensions in the model. The parts all have the same outer diameter, so can easily be made from the same material stock. This year I decided to use precision ground stock to avoid having to turn and finish the outer diameter surfaces. Machining parts on a lathe typically involves leaving a holding allowance which must be parted off and is usually scrapped. As a challenge, I decided to avoid any scrap holding allowance by carefully selecting pairs of parts which could be made from a single piece of stock and parted from each other at the right point during manufacture. The first piece of stock will make the main screw, then the remainder of this piece will make the spacer. The second piece of stock will make the threaded body, with a screw cap being made from the rest of the length. I picked the ER32 collet chuck for this project as it holds precision ground stock well and is less likely to mark the nice outer surface than a 3-jaw chuck. This is the first big project I've made using this ER32 collet chuck, and it has some downsides which didn't work so well. This Morse taper style of collet chuck sticks out a long way from the spindle. The taper is only a Morse 2, so the shaft is quite narrow and flexible. A chuck needs to hold a part rigidly relative to the spindle, or the cutting forces will cause it to bend and vibrate, so flexibility in the chuck shaft is not ideal. Another important lesson I've learned since this project is the problem of using large radius inserts like this for roughing on a small lathe. The combination gives me lots of vibration and chatter, which is clearly not going to work well for removing this much material. To keep the part more stable, I decided to drill a centre and use a live centre in the tailstock. This isn't a good example of how to machine a centre though. The RPM needs to be fairly high when establishing the start of the hole, but it's a good idea to slow down quite a bit when the tapered section of the centre drill makes contact. The larger the diameter and the engagement, the more difficult it is for the lathe to avoid chatter, and the lower the RPM should be. With the live centre installed, the material removal is much smoother. This section of the part needs to have a lot of material removed to get to the basic major diameter of the screw thread. This insert is rated at 400 meters a minute cutting speed, so I increased the spindle speed to remove the material faster. The depth of cut is way too low for this roughing insert though, so the chip doesn't break and gets tangled very easily. The large radius on this tool contributed to the chatter problems I had, but it also creates another problem. The more a tool is engaged with the work, the more chatter problems it has. When a tool with a radius this large is cutting into a corner, at the end of each cut, the full outer edge of the radius is engaged, and it gets harder and harder to cut right into the corner without the chatter becoming overwhelming. As a result, there's a build-up of hard-to-remove material in the corner that will need to be removed later. I cleaned out the corner by repeatedly approaching it from different directions, first axially, then radially. It should be easy to see and hear how the chatter gets worse as more of the radius is engaged with the material. Now the screw section is the correct diameter, I need to prepare it for threading. A chamfer the full depth of the thread is useful to avoid a messy thread start and helps it engage. The thread start is a long way from the chuck, and getting the chamfer to the full depth of the thread took quite a lot of engagement, so it was very difficult to avoid chatter. Single point threading is generally simpler if there's a gutter at the shoulder end of the thread, and this is especially important when the threading tool is going to start each pass at this end. It's not usually a good idea to run the lathe nearly this fast when cutting a wide groove, but when I've tried running it slower with tool steel, the lathe just stalls. I'm going to cut this thread away from the chuck using a right-handed internal threading tool at the back of the part. I went into a lot more depth about how to set up the lathe for this technique in the video on making a boring head arbor, so go and check that out to learn more. The lathe is already fully set up with the correct change gears and the compound set to the correct feed angle. All that's left is to touch off to locate the surface and move the tool into the gutter. I then engage the threading feed, locking the carriage position to the spindle rotation. This has to stay engaged until the thread is complete. I should have checked the pitch with a thread gauge after the first pass, but I was distracted by the filming and forgot. It's worth doing no matter how straightforward the lathe setup is, as it saves a lot of heartache and scrap if the mistake is caught at this point. The first few passes in a thread are easy because only the point of the tool is engaged with the material. As the threads get deeper, more of the side of the tool is engaged, the cutting forces get larger, and it makes sense to use lubricant to help the tool cut more smoothly. I tried out using WD-40 to lubricate the threading tool. It didn't work nearly as well as heavy cutting oil on steel, so I won't be using it again. The boring bar is quite extended to allow for the length of the thread. When combined with the flex in the part due to the ER32 collet chuck, the overall flex in the situation means deep cuts were not possible, so lots and lots of passes were required. Once the thread was fully formed, I checked the pitch diameter with thread wires, the most accurate way to check and necessary as this is a custom thread. The other corresponding part that this thread will fit into hasn't even been made yet, so it isn't available to check the fit in the usual way. O-rings looped over the ends of the wires is a really great way to hold the wires in place, leaving both hands to hold and adjust the micrometer properly. They work great as they're available in a good range of small sizes to suit different threads. Thread wires work because the round wires rest firmly against the flat sides of the V-shape and provide a definite measure of the pitch diameter independent of the geometry of the crests or troughs of the thread. Some calculations are required to work out what the measurement should be for a custom thread. If there's enough interest, I can make a video explaining how I did them. The measurement checks out, so I can now disengage the threading feed. With the compound and cross slide restored to their starting position, I now do a turning pass with the threading tool along the full length. This removes any protruding burr raised on the thread crests by the cutting operation. A final pass with the lathe file smooths off any remaining lack of evenness on the crests. One side of this part has been completed, and now I want to machine features on the other side. To do this I need to part it off from the length of stock currently held in the collet, but parting through all the way to the centre of such a large steel stock will be very difficult on this lathe. Instead I use a collet block to hold the screw thread and cut it off the rest of the stock using the bandsaw. I'm now going to work on the other side of the part on the lathe, which means switching to a smaller collet. When changing collets, it's very important to make sure the taper is completely clean, as the collet won't run true if there's the smallest particle of metal in the tapered bore. To machine this end, I switched to an insert with a much smaller radius. The reason I switched will be more obvious shortly, but it clearly works better at facing than the large radius insert I was using. To make sure the jack can be adjusted while securely supporting a piece of work, a rotatable cap will sit on top of this end of the screw. The area where the jack screw and the cap are in contact needs to have a geometry which keeps them rigidly coaxial but allows free rotation. This requirement is met by machining a shoulder to locate the cap. The shoulder needs to be fairly wide as it will carry the full load of the jack. The outer diametric surface next to the shoulder will act as a bearing surface, with the inner diameter of the cap sliding against it. It allows the cap to turn, but keeps it concentric. The small radius insert helps keep the inner corner of the shoulder nice and square. The lathe work is all done, and the final operation is to add radial through holes to make the screw easy to adjust. I want to be able to hold this round part while I drill it, and then rotate it by 90 degrees for the next hole. The most straightforward to do this with high accuracy is to use a collet block, and due to the size of the part I need the largest collet block I own, an ER32 square block. This larger collet block makes it difficult to hold in a vise mounted across the table, as this particular vise only has a few usable clamping points, so I'm mounting the vise along the table instead, so I can use the clamping points at the end. The adjustment holes need to be drilled through the diametric centre of the part. As the stock was precision ground to exact diameter, I should be able to find the centre easily by locating from one edge if I use an edge finder to find that edge. The centre finder kicks out when it locates the edge of the part, at which point the spindle axis is exactly half the centre finder's diameter from the surface. I adjust the dial to compensate for half the diameter of the centre finder, then wind it half the diameter of the stock. It should now be exactly at the centre of the line of the part. Time to remove the centre finder and install a drill chuck to make the holes. I established the location of the hole with a spotting drill. A spotting drill is a lot more rigid than a twist drill, so should be able to establish an accurate hole start on a curved face by pecking and using minimal force. The exact location along the axis is not critical, so I can eyeball the centre of the cylindrical segment. To locate the next hole, I turn the collet block 90 degrees, realigning using the clamping nut against the side of the vise. This project was before I built the vise stop, which would have allowed me to repeatably locate the collet block more flexibly. Once the hole starts have been located, it's straightforward to drill them through with a twist drill. These holes will allow a pin or wrench to be used to turn the screw when it's hard to reach in a complex work holding situation. Flip the block back 90 degrees to drill the other hole, which will cross through the first hole halfway. The second hole passing through the first doesn't seem to be a problem, as half the hole length was there to hold the drill steady. I reduced the pressure as the drill was re-establishing the hole after the halfway gap, and pecked a few times to make sure the hole started cleanly. This is the final operation for the main screw, so on to the next part, the cap, which will be machined from the end of the second piece of stock. The cap is going to sit on top of the screw head, with the outer rim of the cap resting on the shoulder and the inner diameter of the pocket in the cap in contact with the smaller diameter. The pocket will need to be slightly deeper to ensure there's no obstruction which interferes with the rotation. There'll be two main features in the top of the cap. A large centre can support a ball bearing, which makes it easy to provide stable single-point contact with the part being supported by the jack. The second feature is a groove, which allows the jack to very stably support horizontal cylindrical parts. This second piece of stock is the full 20mm diameter again, so I switched back to the 20mm collet to hold it. This face needs to have a good finish, as it will be one of the most visible final surfaces of the tool, but also because it will come into direct contact with parts supported by the jack and needs to make clean contact with flat surfaces. It made sense to me to cut the centre first before the V-groove, so the centre drill would cut more smoothly. There was the usual problem with wanting to slow the speed down to reduce chatter, but needing plenty of motor power to keep the lathe moving. The most obvious way to cut a V-groove is to mount the part at 45 degrees and use the 90-degree angle on the edge of a square end mill. I kept the vise mounted on the mill table the same way as before, and used the same collet block as it seemed the most secure way available to hold a round part really firmly. To make sure the groove is aligned with the centre of the cap, I need to locate the edge of the part. Rather than use an edge finder, I used a slip of paper held gently between the cutter and the part. As soon as the space between the cutter and the part reaches the thickness of the paper, the force of the cutter pulls the paper away before doing any damage to the edge of the part. From the edge I used the handle graduations to track to the centre line, then half the groove width higher to start cutting. From this position the quill needs to be fed down for each pass until it reaches the centre line, then the same distance beyond the centre to establish a groove that is symmetric across the centre. My small mill has a reasonable amount of power, but is way too flexible to remove a lot of material fast, so I had no choice but to take a lot of passes. The finish seems reasonable, but with the cutter moving in this direction, the chips can easily get caught between the cutter and the machine's surface, so it would be better to have chip evacuation. However, evacuating chips with a jet of air blows away cutting oil, so it isn't a perfect solution. At some point I'd like to try a mister, which provides a jet of air to clear chips with a light mist that both cools and lubricates, but at the moment my shop isn't set up to handle that much mess. The cap surface geometry is done, so just like with the main screw, I need to saw it off the rest of the stock and start work on the back. This side needs a pocket deep enough to accept the top of the screw head with a 2mm wall, so its inner diameter is a slip fit on the screw head. I need a centre hole to start machining the pocket, but I don't want to drill it any deeper than the 2.5mm depth the pocket needs. The cutting point of this boring bar sticks out just enough that I can start taking light passes with it to remove material. This seemed quicker and less risky than trying to open up a larger but very shallow hole with a twist drill, but it didn't work out as well as planned. At this point there seems to be plenty of clearance all around, but with each pass the lower side of the bar closest to the camera is getting closer to the rim of the part. I experimented with cutting towards the centre as it initially seemed to cut more smoothly, but a couple of passes later and it didn't seem to make any difference. Once I've made a few passes, the back of the boring bar gets very close to the outer part of the face and starts to rub. It was subtle at first, and I didn't immediately notice, but it was clear this situation wasn't going to work for the depth of pocket I needed. It looks like using a larger twist drill is unavoidable, so caution is required to make sure it doesn't go too deep. This is way too fast once again, but that's just one of those lessons I hadn't learned yet when making this tool. This left enough room to get almost all the way to full depth, but not quite. The pocket isn't yet full diameter, and allowance is left to clean up the inner diameter surface once full depth is reached. Even with the large hole, there still isn't room to use this longer boring bar, so I had to switch to a smaller one and deal with the fact that it is less rigid. The pocket needs to be 2.5mm deep to make sure the two parts are only in contact around the outer edge, as this makes it more stable. Once the back face of the pocket was established at the right depth, I switched back to the larger boring bar to bring the diameter to the correct dimension. This is the most critical surface of the pocket, so it's important to machine it accurately and get a good finish. The other half of the second piece of stock is going to be used to make the base. It's a straightforward cylindrical part with a flat top and a threaded hole down the middle for the main screw. The bottom is machined to match the same stacking geometry as was used for the top of the screw and the bottom of the cap. This helps ensure that the parts can be stacked in whatever order the machinist chooses. Unlike the previous two parts, this part doesn't require any extra material for chucking, as almost all of the machining is internal, so the full length of the stock will be used without any wastage. The centre drill and first pass pilot drill went okay, though I was running the lathe quite a bit faster than ideal. The hole is many times longer than its diameter, so beyond a certain depth the chips don't clear themselves well anymore, and the drill has to be frequently withdrawn, cleared of chips and re-lubricated with cutting oil. Learning to drill holes in a small lathe has been a lengthy learning process ever since I first started out. With my early projects I blunted a lot of twist drills by leaving them in the part way too long. Gradually I learned to clear the chips often and apply new cutting oil. Later I learned to listen to the sound the twist drill makes and spot how it changes if the temperature is getting too high or the chips are clogging up the flutes and getting compacted. I've improved my technique a lot since I recorded this footage, especially when it comes to getting the speed right. The lathe is running much too fast here, which causes unnecessary noise and rubbing and reduces the life of the cutting edge. Once the pilot hole was established all the way through, it was time to bring it out to 10mm, which is the largest twist drill size this lathe can reasonably manage. For this job I made a very poor choice of twist drill with this blacksmith's drill. Even though the drill is brand new, it doesn't have a sharp enough edge to cut the steel. I probably made this problem worse because I was running the lathe too fast and what little cutting edge the drill had was quickly worn away. I even applied enough cutting force to push the part further into the collet without successfully removing any material. Rubbing tool steel with a blunt tool like this can lead to even worse problems, as it can cause the steel to work harden so much it's almost impossible to cut. I replaced the black drill with a coated high-speed steel drill pre-ground for tougher steels and was able to get this to cut. I stopped to cool and lubricate the drill very often to try and avoid losing the cutting edge. Unfortunately I was still running the lathe way too fast for this size of drill. As I only have a 10mm drilled hole and small boring bars that fit into this are flimsy, I tried a different approach using a heavier boring bar to gradually bore out radially to the final diameter rather than bore along the length. This technique worked but was way more fiddly than I expected and had no real advantage over boring along the axis, so I won't bother using the technique again. Once again I've reached the limit of what I can do with this situation, as the back side of the boring bar is starting to come into contact. Fortunately this time it doesn't matter. The boring bar has established enough clearance near the top of the base to ensure that the screw can be tightened flush against this face. To tighten up the other end of the part and bore the rest of the geometry, the part needs to be flipped around. This end will be the bottom of the screw base, and the first step after facing is to increase the inner diameter of the bottom half of the part. I'm boring out the lower half to a clearance diameter for a couple of reasons. Firstly, cutting a single point thread to the full length of this narrow diameter would cause a lot of problems. A threading tool which fits into this narrow diameter needs to be fairly thin, and so is quite flexible. Combine that with it being long enough to thread the entire length of the bore, and it would be so flexible that cutting accurately would be very hard. Many shallow passes would be required without it being easy to tell how well the process was progressing. Secondly, the length of the base is far longer than the thread requires for good stability and strength, so it makes sense to reduce a threaded section to a more suitable size. I used the scale on the hand wheel to check how far each pass was bored, but after a few passes it became very obvious from the sound when the cutting edge was getting near the shoulder, forming inside the part. The final step on this end is to replicate the same geometry that I machined into the underside of the screw cap. This was the geometry that matched the shoulder on the top of the main screw, and I'm replicating it here to add extra flexibility. This geometry will also match the top of the spacer I'm making for this jack, so the machinist using the tool will have the choice to use the spacer underneath the base to elevate the whole tool, or between the main screw and the cap, increasing the height but keeping the two threaded portions lower down. I used the compound to put a slight chamfer on the corner of the stack fitting to ensure the stacked parts would fit together easily in difficult situations. Now to flip the part back round and cut the thread. The inner diameter to be threaded needs a couple of passes with the boring bar to tidy it up and bring it to the right diameter. This also helps to make sure it's properly concentric, as the part has been rechucked and this style of ER collet chuck isn't nearly as repeatable as a genuine lathe collet chuck like a 5C, which is specifically designed to hold parts on a lathe spindle with good concentricity and high repeatability. Off camera I coloured the bore with green Sharpie. As usual, this is to make it easier to check the pitch of the scratch pass, but then I promptly forgot to actually check it once again. Fortunately, the setup of the change gears was untouched since I cut the first thread, so there was very little way this could go wrong, but I try and make a point of checking every thread I cut. I'm cutting this thread using a conventional right-handed internal thread tool, as I don't have a small enough left-handed internal tool which would allow me to thread away from the chuck. To do this safely, I have to extend the tool even further from the tool post to reduce the chance of crashing at the end of each pass. Just like any thread on this lathe, the first few passes can be fairly deep, but as the tool engagement increases, the increase in depth for each pass has to be shallower to keep cutting forces and chatter under control. I didn't catch much of the detail of the threading procedure when filming this project. I've shown the technique for cutting an internal thread away from the chuck with a left-hand tool in a couple of videos. Firstly in the gear cutter arbor video, then more recently in the boring head arbor project. I don't think I've ever done a good job of showing the technique I'm using here. Let me know in the comments if you'd like to see this process explained in more depth. It's much more difficult to measure female threads as I can't use thread wires. Thread micrometers are really expensive and internal thread micrometers aren't widely available, so I don't own any. The only option I have is to try and keep track of the depth the tool has been fed in and check the fit using a matching part. I did the last few passes and the fit checking off camera as it got pretty boring, but eventually I got a smooth fit I was happy with. Just like with the first thread, I returned the tool to its starting position, and with the threading feed disabled, I used the tool to clear any protruding burr from the crests. The screw base is now done and the 3 completed parts are enough to make a working tool, but there's one final part to add to the set. The spacer won't be necessary every time the tool is used, but it will make it a lot more flexible. The spacer is essentially a tube with a clearance hole through the middle and the stacking geometry machined into both ends. There are no new operations needed for this part. Every feature is one I've already machined into one of the other parts, although I did make fewer mistakes and misplanned steps in this one. I did a slightly better job of drilling the pilot through hole this time. When drilling steel, it's important to make sure the drill has enough engagement, as too little will cause rubbing and work hardening. Sometimes this means feeding the drill in a way that feels very hard and fast, but which in practice doesn't cause the drill to heat up nearly as fast and causes less wear. I still have a long way to go to improving my technique with larger drills. In my early projects I made the mistake of doing many passes with small increases in the size of the twist drill. The problem is that only the very outside part of the cutting edge is engaged with the material, so the edges cut and wear unevenly. As much of the cutting edge should be engaged as possible for good drill performance, so a pilot drill size should be chosen which is just larger than the web of the final size twist drill. It's very rare that more than 2 drill sizes are needed on a small lathe. I bored out the through hole to be a comfortable clearance diameter for the main screw thread, though in practice the main screw will rarely need to pass through the spacer. Normally the full length of the screw is contained inside the body of the jack or above it. It makes sense to have a clearance diameter through to make sure that future additions to the jack work well. A future owner might want to add a longer screw to the set, in which case a spacer without good clearance would be less useful. The bottom of the spacer will have exactly the same stacking geometry as the cap of the jack, which will allow the spacer to be used between the top of the screw and the cap, as well as under the main body. Using it in either position increases the overall height of the jack by the same amount, but allows the adjustment to be at a different point in the stack in case it's difficult to reach. The precision and surface finish of this inside diameter is once again important to make sure the jack works well. If it isn't a good clean fit, then the jack will be less stable and smooth to operate. The final touch on this side is to break the corner on the inner diameter to make sure the stacking parts go together easily. The matching stacking geometry needs to be machined in the opposite side to make the spacer complete. It will also be possible to add additional identical spacers to the set, and as long as the stacking geometry matches, they'll all fit together in whatever order the machinist prefers. The spacer was made from the material left over when I made the first part. This means every part of the stock I cut for this project has been turned into a part, succeeding in the goal I set for myself at the start. The only scrap was the chips and swarf generated during machining. The point on this insert is starting to get dull. You can hear the lathe speed dropping due to the higher cutting forces, but I didn't notice myself when I was running the machine, so carried on with a dull insert. Once again, the diameter and surface finish is important for good stacking performance, and once this finishing pass is done, the tool is complete. I'm really happy with how this tool came out, but as it's a gift I never got to find out how well it works for myself. If you're interested in finding out, head over to Craig's workshop to see what he's managed to do with it. I was really delighted that Craig agreed to collaborate on these videos, so many thanks to him, and make sure you go and give him a visit. There's a link at the top right now, or down in the description. My next video will be back to improving the Chinese lathe, so don't go too far. Thanks for watching, take care, I love you all.